Now we're going to put bounds on definite integrals. The only kind of integrals we have is definite integrals. And this is quite similar to a result you see in Calculus 1. So section 4.43, upper bounds for moduli of contour integrals is the title. Remember calculus, you took a Riemann integrable function f on the interval a, b, and that function was bounded in absolute value by some upper bound capital M. Then, if you integrated f of x dx, you got the value of that integral is bounded by capital M times the length of the interval, capital M times b minus a. You'd think about probably areas of rectangles. This is the height of a rectangle, and the function lies entirely under that in absolute value even. And we've got the base of a rectangle is b minus a. So you kind of think of this as b minus a times m. If you were doing Riemann sums and you did some upper Riemann sum, this is the ultimate upper Riemann sum. Whatever the function's doing, it's contained in a rectangle of the height, capital M, and the base, b minus a, in absolute value. So this has physical meaning to you. You can talk about areas in the real setting. So I'm doomed in this setting with any area conversation. But a result quite similar to that holds in the complex setting. So you want to think bound on the absolute value, modulus for us, of the function, and b minus a, that's the length of the interval over which you're integrating in the real setting. We integrate over contours, so lengths of contours will play roles for us. First result, lemma 4.43.a says, if w of t is a piecewise continuous complex valued function defined on the interval from a to b, then the modulus of the integral is less than or equal to the integral of the modulus. And there's a result similar to that from the real setting as well. Let's take a look at the supplements and go through a proof of that. Okay. All right, so let's go through proof where first, if that definite integral, if it's 0, certainly this is true. That's how it holds trivially. The left-hand side is 0. Well, 0 is less than or equal to the right-hand side because it's something non-negative. So without loss of generality, we can assume that the integral is not 0. The case for it being 0 is taken care of. It's an integral of a function of a complex variable. So the value was potentially complex valued. Call that value r sub 0, e to the I theta sub 0, and we're in a setting where that is not 0. That integral is not 0. All right. Well, from this little equation then, we can take this e to the I theta 0, move it to the other side as a reciprocal, so it carries with it a negative exponent, and use linearity to pass that inside and say r sub 0 then is of the form integral from a to b, e to the negative I theta sub 0 constant, w of t dt. R sub 0 is real, so the value of this integral is real. All right. Well, r sub 0 being the real number and being the value of this integral, r sub 0 equals the real part of this integral. Actually, we know that integral is real, so we've got that holding. And the real part of an integral is the integral of the real part. In this setting of integrals of w of t, where t is real and w is complex valued, not with the moduli, but when we simply had integrals of w of t, that's exactly how we defined it. It's the integral of the real part plus I times the integral of the imaginary part. So what we get for the real part of an integral is the integral of the real part. It's how we defined integrals in these settings. Okay, now, so where we leave things is r sub 0 equals the integral of this real stuff here. We know the real part, we're looking at the integrand of what we had previously, the real part of some complex number, the real part's less than or equal to the modulus of that complex number. Think of how you compute moduli. That complex number we're choosing here is e to the negative I theta sub 0 w of t. It's the integrand over here. So the real part of this is less than or equal to the modulus of this complex number. Modulus of a product is the product of the moduli by properties of moduli from way back when. The modulus of an e to the negative I theta sub 0 type thing, that's 1. These are this is a point on the unit circle. Think Cauchy's formula, if you like. You'll expand it in terms of sines and cosines. Cosine squared plus sine squared equals 1. Certainly that's with modulus 1. So we've got the real part of this. We've got this integrand less than or equal to the modulus of w of t. So the r sub 0 equal to the integral of the real part is less than or equal to the integral from a to b of this modulus. You chose an integrand here. It's bigger than the integrand here. That yields a larger integral. It's called monotonicity of the integral. That's a calculus 1 result. We okay using calculus 1 here? As long as the integrals are real, we are. Yeah, everything's real. The integrand here is real. It's the real part of something. And the integrand here is real. It's the modulus of something. So we're okay to use that result from calculus 1. Now, if we'll just glue these things together, we had r sub 0 equal to this integral up here. We can take the modulus of that because it's a real number, we know from above. We can bring the constant e to the negative I theta 0 out of the integral. We have linearity of the integrals in that sense. Write this as a product of moduli, but you know the modulus of this is just 1. That produces this thing here. And we just saw that r sub 0 is less than or equal to the integral of the modulus. So we use that value. That inequality is related to r sub 0 here. And the last little piece is the claim that we were making. So we've established this little inequality based on 2 things. R sub 0 equals this by that line of argument, and R sub 0 equals that as stated in the previous line. So that's the logic on that one. Okay, next result, back to the notes. Probably could have stayed there. Next result is a slightly more general result. Not really. It says, okay, so suppose instead of w of t, we integrated a function f of z. Well, you integrate functions of f of z by producing something of this w of t form. So theorem 4.43.a says, let C denote a contour of length L, and suppose that a function f of z is piecewise continuous on C, so we can take the integral. If m is a non-negative constant such that f of z in modulus is bounded above by this capital M, that's awfully similar to our initial conversation about real functions, then the integral over C of f of z dz in modulus is less than or equal to m over L. That's virtually the same thing we had upstairs in a conversation of the reals, except now instead of b minus a, we've got the length of contour C. Well, b minus a was the length of interval AB up there in the real setting. This is quite easy to establish given we already have that previous result established. It's just a matter of really fiddling with the notation. Okay, so with the contour as z of t, parameterized with respect to t ranging from a to b, we have the integral over c of f of z dz is rewritten in terms of an integral from a to b of f of z of t, z prime of t dt, definition of such integrals. So in the previous result, we saw the modulus of the integral of w of t is less than or equal to the integral of the modulus of w of t. So that's exactly what we have here, where w of t is a touch more involved. W of t is the function f of z t, z prime of t. So take w of t and replace it with this. in that previous lemma, and it produces exactly this inequality. So we've converted the integral here into an integral there using the previous lemma. All right, you like this integral? Yeah, the integrand is real valued because it's the modulus of something. So this last thing's a real integral. We were told we had a bound on f. The f of z, or f of z of t, is bounded by m. F of z of t is bounded by m in modulus. Hypotheses there. So we can rewrite this integral as integral from a to b, f of z, z prime of t. We've got the bound of m. This is a result from calculus, probably calculus 1. So we've got a bound. We've replaced the integrand by a larger function, monotonicity of the integral, it's likely called in calculus 1. We'll bring that constant of m out of the integral. Now we're left with an integral from a to b of the modulus of z prime of t dt. Ring a bell recently? That's what we define. I guess it was section 39. That's what we defined as the length of contour C. So we've got the inequality. Modulus of the integral is less than or equal to m times this particular little integral. And that little integral there represents L, the length of contour C. So there you go. We've got the modulus of the integral. Modulus of the integral is less than or equal to m times L as claimed. So let's use that in some examples. Okay, so we're going to get bounds on integrals. These could come in homework exercises that show the following integral is bounded by the given bound. Here we're given an integral and we're looking for a bound is the way this is stated. Let C be the arc of the circle mod z equals 2 from z equals 2 to 2i. Okay, by this stage you ought to be getting the ability to visualize that. So let's see, we've got the circle, radius 2, centered at 0 in the complex setting. And we're taking the piece of it from z equals 2, positive real axis, to z equals 2i, positive imaginary axis. So for that circle, we're taking, if you let me talk like this, it's not entirely legitimate, we're taking the piece of that circle in the first quadrant. So we're taking a quarter of the circle. It's in the quadrant of the complex plane where both real and imaginary parts are positive. So it's a quarter of a circle of radius 2. We'll be needing its length here shortly. So there's the arc C. They want us to integrate over C the function z plus 4 over z cubed plus 1 with respect to z, and the goal is to find a bound on that integral. All right, if c is a complex number on this arc, then it has modulus 2. It's a circle. Say commonly abbreviate them. It's a circle mod z equals 2. So let's see how big the numerator could be. Z plus 4 in modulus is less than or equal to the modulus of z plus the plus 4, or modulus of 4. It's a triangle inequality. And we know mod z is 2, so we get an upper bound of 6 on the numerator. Okay. To get an upper bound on the quotient, we need a lower bound on the denominator, because we'll do a reciprocal thing, and reciprocals reverse inequalities. So we need a lower bound on z cubed plus 1. Modulus of z cubed plus 1 is greater than or equal to modulus of z cubed minus 1 absolute value of, I guess it was corollary, this has been a while, corollary 1.4.1. It's a consequence of the triangle inequality. But we get the inequality in this direction, see corollary 1.4.1. And we know mod z is 2 when z lies on the contour. So we get 2 cubed minus 1. That'd be 8 minus 1 is 7. Absolute value of, in this case doesn't do anything, produces 7 as a lower bound. Okay, so if we'll take reciprocals of both sides of this, we'll see 1 over modulus z cubed plus 1 is less than or equal to 1 over 7. Reciprocals reverse inequalities of real numbers. So we do have an upper bound of 1 over z cubed plus 1 modulus of 1/7. So we'll paste these two pieces of information together. We've got an upper bound of 6 on the numerator, an upper bound of 1/7 on the denominator. We got, if you like, numerator times 1 over denominator. But we get 6/7 as the bound on the function when z is an element of that arc C. So we'll call that M. We need to find the length of contour C. Well, like we said, it's 1/4 of a circle and radius 2. Circular radius 2 has circumference 2 pi r, 2 pi times pi. We got 1/4 of that, so we'll divide the whole thing by 4 and pi. So the length of the contour is 4 pi over pi. I'm sorry, 4 pi over 4 is pi. So L is pi, M is 6/7. We know by the theorem that the integral in modulus is bounded by such M and such L. So the value of that integral is bounded by 6 pi over 7. Okay, so with rational functions, this will be the plan to find an upper bound on the numerator and a lower bound on the denominator because of the reciprocal behavior of inequalities.